Check. One, two, one. One. Check. Check one. Check one, two, one. Test.
Are we waiting for that? Are we waiting for the screen? Cancel? Welcome again, everyone, to the Track 2 breakout session on Neural Language Processing. Hope all of you are eagerly waiting to present your experiences today. Please note that, as mentioned, each speaker will have a duration of 15 minutes. During the first 10 minutes, each presenter will present their experiences, and during the remaining 5 minutes, this will be open for a Q&A session raised by the audience. Our first presenter today is Kalaniya Godagamage S. Danoja, paper ID 12, Identifying the Authenticity of Misleading Information in Social Media Using Large Language Models. She holds a bachelor's in software engineering at the Informatics Institute of Technology. Danoja, over to you.
Hi, good morning. I am Samini Danoja. Thank you for giving me this valuable opportunity to present this ICIIT Conclave 2024. My research idea was identifying the authenticity of misleading information in social media using LLM. These are the table of contents that I am going to present during this presentation. In today's digital world, social media has become the primary platform for sharing information, significantly impacting public opinions and behaviors for millions. However, it also a breeding ground for sharing false information, rumors, manipulated contents, posing subtitle threats, decision making, and social unity. As a result, social media conveys a lot of false and misleading information in social media nowadays, and it is difficult for people to identify what is true and what is not on the information shared online. And this will lead for confusion and uncertainty about the reliability of the information that are shared online. And also this leads for a loss of confidence within the people that are shared, the information that are shared on internet. There are many types of information in misleading information, such as misinformation, disinformation, and fake news. Let me tell about the difference between these types of information. Misinformation is false information which is spread unintentionally. That means it doesn't have a target audience. Then disinformation is false information which is spread intentionally. That means it has a target audience. Then fake news is false information which is but it was taken from the real news content and spread unintentionally. It also a subcategory of disinformation. These types of information lead into significant society harm. In recent years, many researchers have done research on this domain because this is a major problem for society nowadays. By doing the research, I have found some research gaps. Let me tell about the research gaps that I have found. Most current technologies oversimplify information by categorizing it into either false or true, but I have used the multi-classification. That means I have classified it into true, false, and partially true. In existing researchers largely focus on detecting false content without deciding the underlining the intent of the context. This project seeks to fill the critical gap by developing a sophisticated system that only identify misleading content but also categorize it as misinformation and disinformation. This approach improves the accuracy of the content analysis by providing a more detailed understanding of the subject matter. Now I will talk about the methodology that I have used. First I have taken the data set. The data set that I have used is fake real news data set, which consists of USA political data gathered from the politicalfact.com in 2020. This is the whole workflow of my project idea. First, we have implemented the model for the detecting the misleading information, whether it's a false, true, or a partially true. Here, I have used the bidirectional GRU model to implement the model. Then after I have taken the model output and do the pre-processing and feature extractions and checking whether if the information predicted as a false information, then we are checking it whether it is misinformation or a disinformation. Here for this I have used a text log called Python library because I couldn't find a proper data set that has been classified into various types of misinformation. So the reason I have used this text log library is, in this text log library there is a thing called feature called subjectivity. That subjectivity can measure the how many people involvement in that text. That means as I mentioned, the disinformation is intentionally based. That means it has a target audience. Then that means it has a target person. So subjectivity can, if the subjectivity high, that means that false information is a disinformation. By using these two predictions, I am giving a prompt to the GPT and giving me a detailed reason. In next slide, I will talk about how LLM use in my project idea. This is a small demo of my project. First, the user input the content. Then, using the model reviewability detection model, it will show us the user input content is false. Then if that false, then it will check whether is it a mis or a disinformation, and it has predicted as a misinformation. Where the LLM is used in the summary part. Here the large language model GPT Turbo is utilized to generate the detailed explanation based on its prediction by using a prompt that requests the model to elaborate on these predictions. GPT-3 provides a comprehensive insight into the reasoning behind its output. This approach allows for a deeper understanding of how a model interprets and responds to given inputs. These are the limitations in my project. This research only focuses on the text written in English. This system only allows the user to input the text format content. The model was trained only by using the news content that was collected in 2020. This is the main limitation. Distinguish between the disinformation and misinformation is challenging due to the conceptual misunderstanding and interpretation inaccuracy, which can lead to misclassification. Because here I am using a Python library to predict identify the disinformation and misinformation. These are the future enhancements. Creating a data set that can be accurately identify various types of misleading information. Improve the model to identify different types of languages. Improve the model to handle the various types of posts that are spread on social media. In the conclusion, my project system name is Veravvisor. It is an innovative system designed to detect and differentiate between misinformation and disinformation on social media. This system helps to improve the digital literacy and prompts the credible information consumption. The research aims to address the gaps in existing detection tools by implementing a multi-classification system that distinguishes between unintentionally and intentionally misleading content, and this system validates and provides an explanation summary of the prediction by integrating LLMs with the model prediction. This is the end of my presentation. Thank you.
Okay, thank you very much. Semini, right?
Yeah.
Semini. I ask the audience for any questions if you want to ask.
So, a really interesting idea, bringing out misinformation and disinformation and giving people more education in order to make choices about what they read online. I wonder, given some of the limitations you've identified, what maybe would you do next? What would be your future work if you were going to continue the project?
The limitations are like the main limitation is I am using a text lab called Python library. Here that the feature is the subjectivity. I am taking an assumption there. It will be misclassification. It will goes to misclassification because this is my final year project. With the time frame I couldn't make a data set. So my first step in the future was making a data set for identify various types of misinformation.
Anyone else to ask any questions? Any clarification? Just one question. Now, say you said you did this classification. It was only true and false, but you went to partially truth also, right? By doing that, you have any idea how much more percentage that you went into the correctness of your data or correctness of your prediction?
My model gave me like around 79%. So I just take the fake news real data set. It has 6 class labels. I have reduced it to 3 because most of the audience can identify the partially true and false. Other types it cannot be identified. So the reason was I just manually divided it. Actually, I don't know the presentation. It's some
Bigger data set to have it more accurately.
Yeah.
Right? How big is your data set?
It's like around 10,000.
One last one for me. So there's been some really interesting work in conspiracy theory detection with LLMs in recently. And one of the things that they found was different types of conspiracy theories and different types of misinformation can be classified. Some can be classified really accurately, whereas others not so much. I wondered if you looked at what types of misinformation and if there was anything interesting that the outcomes in.
There are various types of misleading information as misinformation, disinformation, fake news, malinformation, anti-information. There are various types. In my project, I only focus on the misinformation and disinformation because the misinformation is unintentionally, that means it doesn't have a target audience, just spreading. Disinformation is intently based, that means it has a target audience and somewhat harmful for the society. The fake news is false information that was taken from the real news content and spreading. Then malinformation is true information, but it taking the target audience personal things and just spreading it for harm to that person.
I was more meaning the domain. So, for example, one of the things with conspiracy theories is there's a lot of data sets about COVID misinformation, and so some models tend to be really good at picking up misinformation about COVID, whereas they're not so good in other domains. And I wondered if you noticed anything similar. Sorry, I should have been clear.
Thank you.
Does it have a way to trace down the route where the source is originated?
Sorry, I didn't.
Does it have a capability to trace down the route where the misinformation has originated?
Whether it can be traced up to the root of where it is coming from.
Actually, I'm not pretty sure because I'm just taking the 2 prediction and just given the prompt. Yeah, I'm just telling the prompt to use these 2 and giving me the reason. Sometimes it gives the root, but sometimes it doesn't give the root because I just using the GPT-3 actually.
Right. So, do you have any idea of making it with ChatGPT 4?
Uh,
The latest version? Or-
Yeah, for my future enhancement, I will go.
Right. Any other questions? Thank you, Semini. So,
Thank you.
for this presentation.
Before moving on, please note that if there are multiple speakers, the speaker that is called up on stage, please introduce the fellow participants as well. Next up, we have Nabila Fahmy, paper ID 21, Enhance Authorship Attribution through Machine Learning and Stylometry in English and Romanized Sinhala. She is a second-year AI and Data Science undergraduate from the Informatics Institute of Technology. This is an automated system to determine text authorship using machine learning and NLP. Nabila, the stage is yours.
So you can
Yes, introduce.
Good evening. So I'm Nabila Fahmy, and I'm a second-year undergraduate here at IIT. And this is Adipa Gunathilaka, and we are presenting our work on a second-year group project. Our project is an authorship attribution system for both English and Romanized Sinhala. And our problem definition is as follows. It is a non-domain specific, robust authorship attribution system that uses both stylometry and machine learning for English and Romanized Sinhala. So what is authorship attribution? It is a process of identifying an author for a specific text. And stylometry is a process of identifying features within that text that enhance authorship attribution. So this could be semantic, syntactic features, things like the way they write, how their words are spaced, or even their use of vocabulary. Let's move on to our research gap. In our research gap, we found that previous studies that focused on authorship attribution classified text into a specific corpus of authors, the predefined authors. And it does not provide a mechanism that can classify a piece of text into whether it belongs to a particular author or whether it does not. And that system does exist only for a very small corpus of text messages. So there's a huge domain specificity, and as a result, we can find a big research gap in that area. Further, for Romanized Sinhala, there's not a single bit of research for authorship attribution done on it. And given that Romanized Sinhala is the primary mode of communication among young adults here in Sri Lanka, it is important that we do have research on this area, as it allows for better identification of text authorship in this field. So overall, our project aims to create a non-domain specific, robust authorship attribution system for both Romanized Sinhala as well as English. So this is our data overview. So we had two main models. For the English, we used a random forest classifier. And for the Romanized Sinhala model, we used a random forest regressor. So the English data set consisted of two main data sources. A block data set, which is a publicly available data set that contains many JSON files, and only the author name, author ID, as well as the text were extracted from these data sites. And the tweets data set, which is also a publicly available data set that consists of cleaned tweets from many different authors. How this worked was we had a particular text that was selected and a random selected text that may or may not belong to the same author. Then the features for both those texts were extracted, and the similarity scores between those features were then computed. These were all embedded into a final data set, giving a label on whether it belongs to the same author or not. Then the final data set contained 883 separate instances, where duplicates, after removing duplicates, and features that had a total variance of less than 0.05 throughout the entire data set.
So for Romanized Sinhala part, we used WhatsApp chats, because in Romanized Sinhala we don't have much publicly available data sets. So we take steps to take explicit consent from our research participants when we use the WhatsApp chats. And we removed the sensitive messages, went through the chats message by message, and also obscene messages. And then we shuffled, when we take a single chat, we shuffled the messages in that chat to further increase the privacy. And then for feature extraction, we have developed feature extraction strips. I will go for them in the next slide. And in this, in feature extraction, we take different features like text edit distance between two given WhatsApp chats, and these features are combined into a single CSV file, and that will be the final training dataset, and that dataset contains around 400 records. So we can move to the implementation details.
So the workflow for the English model is where the user sends in two texts, one of an author that it suspects the anonymous text to be, and then the anonymous text is input. The features of those texts are then extracted. The following features, which is average sentence length, punctuation frequency, part of speech tagging frequency, which is basically every part of the sentence is tagged as a noun, a verb, an adverb, and its frequency is calculated. Then we have a function of word frequency. These are commonly repeated words. So is, are, the, and passive to active voice ratio in how they write. Then an n-gram transition graph was built for each of it, and the following features from the n-gram transition graph was extracted. The number of nodes, the number of edges, the average degree, as well as the density of the n-gram transition graph was computed. Then the type token ratio to measure lexical diversity and how much lexical variation is there within the author's work. And there was a pre-existing gender prediction using an LSTM model. And then the detection of if the author uses double spaces after a full stop. Then the similarity of both these, both sets of individual features are computed, that is using absolute difference. Then it is sent to our random forest classifier for analysis, and then the results are output.
So for the Romanized Sinhala authorship attribution model, we use both text from a suspected author and anonymous author, and then features such as typing pattern similarity, English to Sinhala word ratio, and global alignment similarity is extracted. And what I mean by typing pattern similarity is when we take two texts, one author may write a given word, a given phonetical word in using different kind of spellings than the other author. So I'm calculating the text edit distance between those same phonetical word written in different spellings, and that text edit difference is the typing pattern similarity. So to identify the same phonetic word, I first transliterate the Romanized Sinhala word into Sinhala. So once we transliterate a Romanized word to Sinhala, then even if it is spelled differently, the Sinhala word will be same. So if a person spelled Gedara as Gedara, or if the spelled that in other way like Gedra, after transliteration it will be the same word Gedara. So there will be a mapping established, and after that mapping we take the text edit distance, and Sinhala to English to Sinhala ratio, we send the text to GPT 3.5 model. We have a prompt prepared, so the model will label the word as whether it is English or Sinhala. After that, we count the number of Sinhala words and English words, and the ratio will be taken. Global alignment similarities, after we identify the same phonetical words, we establish a alignment between them and identify how much mismatch there's between the words. And then those features will be sent to the random forest regressor for identification whether the two texts are written by same author or not. Right. So yeah, when it comes to utilization of LLMs for feature extraction, for Romanized Sinhala, people write English words between Romanized Sinhala, and that's a problem for Romanized Sinhala specific features. For example, global alignment and typing pattern similarity features I explained earlier. So it's essential to remove the English words from Romanized Sinhala text before going on to the Sinhala specific features. So it's important to label the words as Sinhala or English. So for that, we can use a dictionary containing English words and filter out all those words. But I think with the development of LLMs, LLMs capture more writing patterns in human text. So LLMs can filter out, label English text, English words and Sinhala words better than going to fixed static approach by using a dictionary. And then LLMs are good in understanding whether a text is written in British English or in American English. So those features can be extracted using LLMs. And when it comes to testing and evaluation, we have the English model and the performance.
Yeah, so the English model had an accuracy of about 70%, with precision and recall being about the same for both classes. This shows that it is doing a relatively similar job identifying the text which belongs to each of those specific classes.
So for Romanized Sinhala, we have an accuracy of 86% and a precision of 87% and recall of 80%.
You can take another meeting to try that.
So we had limitations working and major limitations is this only works with English and Romanized Sinhala. And for Romanized Sinhala, if the majority content is English words, then it don't work. And accuracy hugely depend on the quality of the text, and that's what I said by previous statement. Majority of words contain in English, that will be an issue. So for the future enhancements.
Yeah, so this system could be used for the Romanized versions of other languages like maybe Tamil or Arabic, and we would be able to enhance the use of LLMs to identify word matches between patterns and even for other future feature extractions. And a language agnostic model could be built which does not depend on a particular language, and we could use explainable AI to properly tell the users what exact features and why we came to the conclusion that we did. And our contributions, as mentioned previously, is that our dataset corpus allows for us to use a most general approach, and it pioneers the Romanized version of many languages. And the random forest classifier allows it to train on values instead of actual textual data. So this allows for a more non-domain specific way, and the Romanized Sinhala attribution system is completely new and has never been done before. Thank you for your time.
Right. I open the audience to ask any questions.
Oh, a really, really interesting talk. Stylometry and stylometry within NLP is a lot of fun. So really, really cool stuff going on there. Really, really interesting talk. Thank you very much. Stylometry in NLP is a very exciting area. I wonder, so at the moment this looks to be applied to text messages, tweets, in other words, short form communication. I've got two questions around that. The first is, what do you reckon your techniques would scale to longer bodies of text, say if we wanted to attribute authorship of an essay or a report? And also, in short form communication, people sometimes communicate slightly differently than they would in other. So do you think your techniques would generalize in that manner as well?
So for the English techniques, there has been a huge body of research, and based on those, we selected the best features. And the blog data set did consist of essays, primarily like words around 500, 600 word, blog posts, as well as blog posts that are more shorter form, like the tweets. And so for the English one specifically, it works. It seems to apply for both relatively well.
So for Romanized Sinhala, people mostly use Romanized Sinhala in informal context, so like Facebook comments, WhatsApp messages, and like so. So it's very unlikely people like write long text using Romanized Sinhala. So we only focused on short message contents. And Romanized Sinhala especially depends on the fact that people write same phonetical word in different ways. So it's one of the main ways we identify the pattern between a given between two authors. So one author may write a word one way, other author may write it differently. So that's how we establish the fact that they are different authors. So we depend on that fact.
Thank you very much.
Yeah, but you said your English is more accurate, but then your accurate percentage in Sinhala is 86%, whereas English was only 70%. So why was the difference?
I think that's mainly due to the fact that in English there were more like features that were extracted, and we could scale it down a bit more. Given our time constraints to have completed the project, we did not really have time to further scale it and see how well it would work with various other features as well.
Maybe Sinhala is into a very limited kind of
The feature,
data set,
yeah.
rather than
English, it's, yeah.
Data set, so accuracy may be more, but percentage-wise,
It's less.
the higher data set. Yeah. So what is the future that you go from here?
So we hope to probably enhance the already existing features that we have, and we'll try to establish more for the Romanized version.
So for the Romanized version, the issue you mentioned earlier is due to the limited scope of the data we had, because in Sinhala we don't have, even though young generation mostly use English text, those texts are not publicly accessible. Either they are in after a Facebook API or Reddit API, or it's encrypted text in WhatsApp. So there's that issue, data limitation. So we have an ongoing project, social media campaign, where we asked users to fill a form, submit in a Singlish message, and its Sinhala translation. We are planning to properly format the finally aggregated dataset and make it open source, so other people can also work on that dataset. And we are planning to further improve the transliteration model based on those texts.
Okay, thank you very much.
Thank you.
Thank you. And our third presenter for today is Dr. Kyle Martin, paper ID 11 on fine-tuning language models for error correction of automatic speech recognition applied to clinical dialogues. He is a lecturer in the AIR research group at the School of Computing of Robert Gordon University. Dr. Kyle, over to you.
All right. Hello there, folks. I am Dr. Kyle, or just Kyle, as I much prefer. I'll be presenting some work performed by one of my PhD students, Gayani Nanayakara, and her PhD supervisory team comprises of Nirmali, David, and myself, and this is some work that we have done at Robert Gordon University alongside the National Health Service Grampian, which is the National Health Service representative in Aberdeen, where we are based. This work targets clinical dialogues. What are clinical dialogues? Well, they're dialogues in a clinical setting. More specifically, they're dialogues with the purpose of capturing some medical information about a patient or participant. So, for example, a doctor may ask about a patient's weight. The patient will reply that they seem to be losing a little bit of weight. And the information captured during this clinical dialogue is used to inform electronic health records about patients. The problem is that these electronic health records are currently a manual administrative process that, among other things, takes up doctors' time. Ideally, we would like to automate some of that process, and with the growth of automatic speech recognition software and systems, most famous of which you might recognize AWS Alexa, and among others, there is a good opportunity to do that. The problem is, in domain-specific settings, these don't always work as well as they should. And so instead of capturing someone's weight, we might capture they've had a loss of wit, which isn't quite what you want. So what we're trying to do is build in some error correction of the transcripts that are captured in order to improve this. There's been some related work in this area. It's broadly split between work that tries to perform correction as speech recognition is happening and correction that tries to apply to the transcripts that are captured afterwards and perform natural language processing to perform that error correction. Now, particularly in this latter category, large language models have shown really, really strong performance, either through training a whole new architecture or much more commonly through fine-tuning. However, even though fine-tuning has less data requirements, it suffers from pretty severe objective and vocabulary gaps when applied to new domains. So that led to some of Gayani's work, where she made 3 contributions. First, she investigated the performance of commercial ASR systems on clinical dialogue. Then she released a clinical dataset for fine-tuning and evaluating large language models in this setting. And finally, she introduced novel supervision pipelines. To inform this work, we used a gastrointestinal clinical dialogue dataset captured by our partner. It's quite a small dataset, as you could appreciate, mostly because of the difficulties in ethical approvals for patients being willing to tell us about their bowel movements. As you can imagine, a little bit shy about that in some respects. So we have 7 audio files. They're each about 5 minutes long, and they contain about 47 utterances. We'll come back to how we enhanced that in a bit. So starting with her commercial ASR evaluation, Gayani looked at the word error rate of commercial ASR systems. What this basically does is it works out the number of incorrect words in a transcription based on 3 operations. How many substitutions have been made, i.e. words that were switched with other words, how many deletions have been made, i.e. words which were failed to capture by the system, and how many insertions, how many words that were inserted into the transcript that weren't actually there in the reference text. So in this example, it would be 3/5, or a word error rate of around about 60%, which is really, really quite high. When she looked at the commercial ASR systems, what she examined 4 of them. She looked at AWS, Microsoft, IBM, and Google. And you can see that broadly, AWS and Microsoft were comparable with about 30% word error rate. But in domain-specific settings, IBM and Google were really doing very poorly. Up to 50% of the dialogue was mistranscribed or had errors in it, which, as you can appreciate for clinical notes, is completely unacceptable because we're recording inaccurate information. So she then attempted to perform some error correction, and she baselined using several language models. In particular, the 2 that worked quite well were T5 small and BART. And the big differentiation here is simply that whereas the pre-training for T5 was a C4 dataset, the pre-training for BART was a book corpus and English Wikipedia. And the result is that BART had marginally more domain knowledge because Wikipedia had some of the medical knowledge in it. We then trained on the PubMed dataset I'm about to describe and tested on the GCD transcripts captured through our various commercial ASR systems. Guyaney, in order to fine-tune the language models, Guyaney collected a data set from PubMed using basically extracting a large volume of abstracts which mentioned gastrointestinal symptoms, diagnosis, clinical examinations, and the patient. And she created 3 fine-tuning tasks for this data set. A summarization task where the input was the abstract and the output was the title. A paraphrasing task where the input was the title and the output was a paraphrase title generated with Google Pause T5, and a masking task where both the title and abstract had random words masked. So next up, that is a copy and paste, we wanted to investigate which self-supervision strategies would best fill the objective and vocabulary gaps that existed in this challenging problem. What this meant was we explored a number of existing self-supervision strategies. Guyaney then implemented some hybrid approaches under the impression that things like masking and paraphrasing might better capture the relationship between substituted words. And then she tried some novel ones, which were domain-specific alterations of some of the pre-existing strategies in order to target that vocabulary gap. For example, medical masking, which instead of randomly masking words, used a medical vocabulary to identify which words were important based on the context, and therefore we should push the model to learn about. And so we had then 3 existing strategies, 2 hybrid ones, and 3 novel ones for a total of 8 strategies, with our primary evaluation being applied on the GCD dataset. If we look at the results for a second, my bolding's not as clear as I maybe hoped it would, but you can generally see that BART performed better than T5, which we can attribute to it having a little bit more vocabulary information. In particular, the mask-filling objective was much better than the other objectives, likely due to the fact it was closer in objective to identifying when words had been inserted, deleted, or substituted, which is excellent, but also that the med mask filling made small but quite significant differences in order to improve the transcriptions. And although the numbers are quite small, it's important to highlight that often what it was correcting was actually medical words, which were the ones most important to capture for the electronic health records. If we look a little bit closer at the word error rate operation statistics, this is an overview with the baseline being the Microsoft ASR system. And you can see that if we look at our mask filling and med mask filling objectives, there's a very significant decrease in substitutions. So it is learning these words are appropriate based on the context. There is very little change to the insertions, so it's not necessarily noticing when to remove words. And there is a very, very minor increase in deletions, so there is sometimes a problem where it will remove words that should be in the transcripts. Now, in some cases, this was getting rid of ums, ahs, and so on. So that's been a bit of a highlight reel. Guyaney's actually applied this to a number of other public data sets, including the Babylon data set, which is an expanded role-playing dialogue data set between clinicians and patients, as well as a Kaggle data set, but I didn't have quite time to go through all the results here. But I've demonstrated our work towards clinical dialogue transcription. We've introduced 2 data sets, and our results indicate that mask filling is the closest objective to filling the closest supervision strategy to filling the objective gap, and that med mask filling plays an important role in embedding that domain knowledge. Thank you very much, and I'm happy to take any questions.
So, audience questions?
I have 2 questions. So, when you did this analysis, did you consider the demography of the patient?
That's a very good question. So in GCD in particular, the patients were usually Scottish patients, right? Because that was who we had access to. However, one of the interesting findings that we identified when we moved to the open public data sets was we could no longer guarantee that. And so we actually noticed a bit of a discrepancy between our performance on the public datasets and our performance on GCD. In most cases, that would be we performed better on our one. However, the opposite was the case. Because it was a mix of American and English people, many of the ASR algorithms worked much better because that's what they'd been trained on. So in actual fact, the GCD had turned out to be a harder data set to start with, and when they'd done their baselining, they discovered that it was a bit easier looking at other demographics. However, it would be really, really interesting to see how this expanded to languages beyond English. At the moment, we're a little bit constrained by the fact there's a small number of data sets. There is one other clinical dialogue data set we're aware of, which is in Chinese, and we did explore for a little while. The problem was that error correction with Chinese characters was quite a big change from error correction with English characters.
So this data set is now available online?
So the PubMed dataset is now available online. The GCD dataset is something you can talk to us to request, because we do have to get some permissions from our healthcare partner. But otherwise, yes.
So your future is to look at other languages to do the same thing and see how...
Yeah. Guyanee's immediate future is now to look at, can we do entity extraction from the transcriptions to try and improve the electronic health records? Because the note-taking is one part of the process, but filling those electronic health records is the next goal. Now that we've got it to a more satisfactory level, that's what she'll be moving on to. But definitely as we look towards further work, more languages and different speakers and dialects are really, really interesting directions for this. So we tried a variety of large language models. It's worth noting that this research started back in 2022? January 2022, I believe. So there were some things that were not as commonly available then as there were now. Also, it was worth noting ASR systems have improved. Guyanee did try with GPT 3.0 and up to 3.5 recently. The problem that they were having was twofold. The first was they were not mimicking the conversation correctly. So conversations happen in turns, and what that GPT 3.0 would try and do is basically try and generate it in one block. The second problem we were having was that it would try and generate more knowledge than was actually there. Many of these clinical dialogues are very structured interactions with short responses between the two, sometimes as little as 10 to 15 words per sentence, and the larger language models tended to generate much more than that. And so that was problematic, and one of the reasons we stuck to PLMs, or pre-trained language models.
Actually, given the results, Google results were pretty good, so you should try with Gemini.
Gemini is something that we're really, really keen. I think it would be really, really good here. But with Guyanee's PhD timeframe, we might have to move on to maybe another one. It would be good. I agree, though.
Thank you very much.
Thank you.
Thank you, Dr. Kyle. And our next speaker for today is Theekshana Samaradivakara, paper ID 10, Long Text Summarization Using Open Source Models. He is a machine learning engineer at Iron One Technologies. Theekshana, over to you.
So hi guys, I'm Tikshana from 91. Number of pages, for that we selected New York Stock Exchange and MX company listed companies. After collecting their annual reports, we start the data processing part. Actually, initial steps we tried existing algorithms and existing models for data segmentation, but the main drawback was the document structure of every company very significantly. As a result, the segmented parts are not good as expected. So we fell back to manual segmentation with the disadvantage of taking more time, but we didn't have much options left, so we went with manual segmentation. To fine-tune our models, we needed label summaries for the annual reports, but since the annual reports are very lengthy documents, using manual effort will take us a couple of months. So as a solution, we found out that OpenAI, other existing models, they were capable of getting good summaries, but we can't use in our application since we are using local resources. We can't run that larger language models in our in-house platform. So as a result, to fine-tune, to get the label summaries, we tried out OpenAI and other open source models like Llama, Falcon and Mistral. So after evaluating the results of the label summaries, when we compare to the cost of the OpenAI and accuracy of other open source models, we went with open source models since the accuracy was much better when we compare to the cost. Yeah. When you come back to model fine-tuning, we went with R&D on several models like BART, Google T5, Pegasus. And when we fine-tune those models, we considered the final results accuracy and the context size. Since there were some good models, but with the lower context size, we tried to increase the context size in the fine-tuning process. And for the fine-tuning, we tried to fine-tune methods, which is normal full fine-tuning process, but considering the local environment, we targeted for parameter efficient fine-tuning methods. Our idea was to reduce memory requirement and the GPU requirement for the fine-tuning and for the inferencing. So such a way we was able to use our local resources more efficiently. As our future work, we intend to fine-tune our local modes on a more broad data sets. Apart from annual reports, we'll try another company reports formats. Yeah. Thank you, everyone. If you have questions, you can ask.
So my question is, you evaluated the cost between the open source and commercialized LLMs. How about the accuracy of?
Take out the whole feedback form. It turned out that some results we can't distinguish OpenAI response to Mistral response. But as a whole, OpenAI is better. But considering the cost, we might need thousands of dollars to get the summaries. But since we are having existing local resources, we can run the local models in our resources. So the cost is actually free. So considering that and the accuracy, we went in our first steps to use the local models.
So you evaluated the cost versus the accuracy.
Yeah.
And then you decided that you go with the cost rather than the accuracy.
Yeah. We compromise the quality.
What is the difference between the accuracies?
In numbers, I can't remember, but from the feedback of the users, I guess for about 60 or 70, they can't distinguish the local model response and the OpenAI.
So the 20% is...
We actually gave them two answers. He didn't tell which one is OpenAI and which one is Mistral.
Okay.
He gave them to the business users.
Yes.
They were saying like both are okay.
Alright.
So that was the, because we gave them directives.
So Mistral is the one you paid and got?
We didn't pay. So Mistral we were able to run on like GPUs.
Okay.
So and especially this problem with we are dealing with annual reports and also board papers.
Yeah.
So board papers are like really
You
huge.
can't. Yeah.
So the cost is, output tokens will cost you more.
So your idea is to summarize these annual reports so that stakeholders have a better view on those.
So we are trying with annual reports. Goal is more towards board papers because we already have a product called board track. So this is towards that. And highly sensitive information, we can't take them out. So all our current products are on-prem for them. So the goal is to come up with local models. So that is what we are trying here. Highly sensitive.
Anything else? Yeah. Go ahead.
Given the focus on confidential information in the documents, did you consider retrieval augmented generation or RAG models as an opportunity? Because they would allow just a local version enforcing the context in the prompt rather than requiring fine-tuning.
RAG, since we are doing text summarization, we have used RAG architecture for other use cases. Since we are using anyway local models, the confidentiality doesn't matter. Since our data remains in our local environment, it doesn't go out to OpenAI or other third party. So it doesn't matter. Yeah.
All right. Thank you very much.
Thank you, Thikshana. And our next speaker is Sahan Vevalvala, paper ID 6, Enhancing Audio Transcription Accuracy with Large Language Models. He is an expert front-end developer focused on creating user-centric interfaces and robust back-end solutions. Sahan, the floor is yours.
So, good afternoon everyone. So my project is based on enhancing audio transcription accuracy with large language models. So in introduction, audio transcription is a crucial thing in accessibility, and for that we have to take the different things like accuracy and to get like different people's accents, and noise reduction is a crucial thing in enhancing the accuracy in audio transcription. For that, I have in my research there are 4 objectives. For that, I have used enhanced understanding of complex language patterns. For that, I have used models to handle diverse linguistic structures, improve their transcription accuracy across various languages and dialects. And for the second objective, I have used training with diverse datasets. So when different datasets, I have used 4 datasets based, and before pre-processing my dataset, it was around 13,000 voice files, and after pre-processing I took it to 90,000 different audio dataset. Noise as well, I had to do some pre-processing. So for improved performance in challenging acoustic conditions, there was many different audio files with noise in backgrounds and other people speaking in different languages. So to improve that, I had to use LLMs and reduce noise and other to get the high precision of the models. So in methodology, there was a data set preparation, model training, noise reduction, and performance evaluation. When dataset preparation, extensive datasets include various dialect accents and background sounds, aim to cover diverse linguistic and acoustic conditions for robust model training. And in model training, use advanced deep learning techniques to instruct large language models, focus on enhancing the model's resilience and flexibility in handling complex language patterns. For noise reduction, I have used sophisticated noise reduction techniques to pre-process the audio streams, improve clarity and precision of model inputs by filtering out background noise. For performance evaluation, I have done with real audio data, so that with transcribed audio, it gets with the real data set, it is different. For results, we have different three aspects I have considered with the current language, current technologies, and with large language models. So for transcription accuracy, current model accuracy with conventional AR's automatic speech recognition systems. In LLM, significant improvement can be detected. Before LLMs, the model accuracy was around to 70%. But with LLMs, it goes up to 90% with real audio data. Then the second aspect is understanding speech in challenging conditions. Because of hard, noisy environments and different accents, current technologies has a huge gap. With the using of LLMs, we can avoid that gap between 60 to 85%. So in emotion recognition or using audio based, we can use currently with the current technologies, we have to go with a deep learning approach or NLP approach to detect basic emotion recognition, and it may be inaccurate because of the NLP and deep learning has many faults in current like gaps in those systems. But with using advanced using LLMs to advanced emotion recognition, using conversation based, we can improve our accuracy from 50% to around 80%. So next we will go to implications. So in implications, enhanced communication tools for the hearing impaired make the essential information more accessible. Then the increased efficiency. So boost productivity in professional environment that requires precision word-to-word documentation such as legal and medical fields. Reliable language interpretation. Provide more dependable resources for language interpretation, ensuring better understanding and communication across different languages. Technological advances promise significant improvement in its overall quality and reliability of automated transcription services, transforming them into essential languages. So in conclusion, significant in accuracy and reliability. Because of using large language model, there is a huge difference in accuracy and reliability compared to normal now using of the transcription data. Then we have the superior performance in challenging conditions. So because of noise reduction and other pre-processing techniques, we have been able to get perform better in challenging environments. transforming into essential tools. The improvement brought by LMs have potential to transform these technology into essential tool in digital society. So when we consider that, when we think about audio transcription in emotion-based conversation, also we can use this tool to audio transcription for NLP and other techniques. Then benefits across, there are so many benefits across different fields like health sector, legal sectors, and call centers, etc. So enhanced accessibility also is another one. So here are my references, and thank you. I'm open for questions and answers.
Audience, any questions? What is your next step?
The next step would be like getting more data sets to get more accurate data, because currently there's a little bit gap between the real data audios and trained, like they are all the audios that are available currently are like acted out audio files. So there's a gap between real audio files and the acted out audio files. And acted out audio files are basically to mostly around 2 seconds audio clips with different people acted out. So that's kind of a little bit gap. So I'm trying to.
Given the accuracies that you predicted with the LLMs, what are the LLMs that you tried with?
So I used OpenAI GPT-4 Turbo and Gemini, but because of after taking there was Gemini, comparing Gemini and OpenAI performed better, so I thought of going with OpenAI further.
So now these are all based on your OpenAI because okay.
Yeah.
Right. Anything else you want to ask?
Yeah.
Was there any specific domain to your audio transcription, or was it multi-purpose?
Yes, so my domain was call center agents, calls between them, and recognizing their emotions based on transcription using an NLP model. Okay, sure.
Thank you, Sahan. Next, we have Deshan K. Sumanathilaka presenting his findings. Paper ID 17. Can AI tackle ambiguity in natural text? Quantitative evaluation on LLMS for WSD. He's a PhD student at Swansea University, Wales, UK. He's currently working as a GTA in the Computer Science Department at Swansea University, and is serving as a visiting lecturer at Informatics Institute of Technology. Deshan, over to you.
Hi, Deshan, you can start. We can't hear you, Deshan. Just a minute, we can't hear you, Deshan.
Recording in progress.
Can you all hear me?
Deshan, can you hear us? Can you hear us, Deshan? Just a minute. We can't hear you.
Okay, wonderful. Thank you for having me today. Good afternoon to everyone. My name is Deshan Sumatilaka. I'm the presenting author of this work. Can AI tackle ambiguity in natural text? A quantitative evaluation of large language models for word sense disambiguation, where we known as WSD. So this work is co-authored by Dr. Nicholas McAuliffe and Dr. Julian Hogg. So we all are from Swansea University, Wales, UK. So this is going to be our content for the day. We'll be discussing about introduction, gap, methodology, results, and discussion, and with the future works. If we have a quick look about the topic, so what is ambiguity? So basically, ambiguity refers to a situation in written and verbal communication where the meaning of a text is unclear or can be interpreted in multiple ways. So basically, we could say if we are having a particular word where a word can be interpreted in different meanings, so there can be an ambiguity. So I'll show some example in the upcoming slides. Right. So in this study, we are mainly targeting on lexical ambiguity. So under lexical ambiguity, we are looking into polysemy, where one particular word can have multiple interpretations. So there are different ambiguities we are discussing the literature, like homonyms, analytical ambiguity likewise. So in this study, we mainly try to tackle polysemy ambiguity by using large language model inspired techniques. So if I take this example, which is the bank is closed. So here you can see the word bank. So here we could say the bank is an ambiguous word where this bank can have multiple interpretation. So basically there are more than like 5 to 6 interpretation for the word bank. So based on the context, we need to decide what is exactly the meaning for this particular word bank. So here we could say the bank can be a financial institute, or it can be a sloping land beside a body of water, where we could say it's a river bank. So when we identify the correct sense or the gloss, we need to know what exactly the context and what is this usage of this particular word in the context. So based on the context or the contextual understanding only, we need to decide what exactly the sense idea of a particular word is. So then what is word sense disambiguation, or typically known as WSD? So this is a computational linguistic task aimed at determining the correct meaning or sense of a word. So this is a very well researched area for English, and as well as for the other languages also, but not in the areas like the low resources languages like Sinhala. So why WSD is important? So basically, we know for the accurate identification of the intended sense of an ambiguous word helps to improve the performance and accuracy of many NLP tasks, mainly like machine translation, transliteration, information retrieval, text summarization, and QA systems, because the intended meaning of a word or the exact meaning of a word play a major role to get an exact meaning of the context where we want to translate or transliterate. So based on the exact meaning is required when we do all these NLP related tasks. So what are large language models? So basically, we know large language models are typically AI models designed to understand and generate human-like text based on vast amount of data. These models are trained on a huge number of data points, and models are typically use transform architectures characterized by their size, complexity, parameter, count. So for these studies, as is an quantitative evaluation, we have evaluated commercial large language models as well as open source large language models, and to evaluate their capability in a WSD task. So why we have selected LLMs? So basically, we know the LLMs are having good language understanding as well as reasoning capabilities. And techniques-wise, we have used prompting and prompt augmentation techniques, then few-shot prompting and chain of thought prompting techniques. So our final approach, we have proposed an approach by using few-shot code prompting approach, which I will be showing you in the methodology chapter. So then, related to the gap, so semantic understanding is a very crucial factor when it comes to the WSD, because contextual understanding is very important, and currently the systems what we have for the WSD is having the concern of having this contextual understanding. And then the data sets wise, it's limited. So basically we are having very limited data set over WSD, which is tagged with the sense tags like SEMCO and Fuse data set. Then we require a proper approach, which is like human-in-loop approach, in order to have a proper prompt or to identify the optimal prompt for the LLM inference. So when we go to the methodology, so here for our work, we are using the Fuse datasets. So Fuse dataset contain the sense tags, training data and testing data. So if we have a quick look on the how sense tags are distributed, basically we have the sense ID, word and the gloss. And for our study, currently we are looking into these three factors, which is sense ID, word and the gloss. So for our input to the model will be a sentence where you have this WSD word between the WSD tokens. So the word will be passed to the model, and we try to follow in this few-shot code prompting approach to identify the exact meaning which is required as our end goal of the output. So here we are having a sort of a training data set. So this work is not focusing on fine-tuning any sort of a base model. So here we mainly try to use general purpose LLM for the baseline tasks like WSD. So rather than fine-tuning, we try to do some sort of prompt augmentation and use some sort of knowledge-based approaches in order to improve the richness of the prompt, such that we could read the our outcome. So basically we use our training data here as a knowledge for our few-shot code prompting approach. So basically we have arranged our knowledge base in the approach like this, where we use training data to create this knowledge graph, where we keep our words as the root nodes and post tags as the first level parent nodes, and all the sentences with sense ID, where some sort of like examples what we require for the few-shot as the child node. So whenever we are having a particular word, we could very easily retrieve the expected senses and sense ID, such that we can use for the few-shot prompting approach. Then this is the methodology what we are proposing here. So this is the final prompt what we have selected in order to test all our LLMs. So this is an iterative approach. Basically, we have tested multiple prompts. We have checked the baseline prompting methodologies, enhanced prompting methodologies. Then we have incorporated different knowledge bases to give the few-shot chances to the model. So here, basically, when we input a sentence, basically we do the pre-processing and we try to identify the sense tag. And so basically with the ambiguous word, we go to the lexical knowledge and we try to identify what are the senses which can be there to represent that particular ambiguous words. Then by using this identified WSD word, we access our knowledge base, try to take the instances which describe different scenarios where as an examples and its respective sense ID. So by combining all these things together, we have created a well crafted prompt in order to do the prompting with large language models. Then based on the output what we received, we do a sort of post processing such that to extract the sense ID in our approach. So this is the fundamental basic pipeline what we have followed to evaluate all the large language models. So this is the prompt what we have used. So this is an very crafted prompt where we have 7 steps, where we initially say this is the word what we want to disambiguate, and we are passing the filtered definition. So why we say filtered? So basically we try to identify the post tag initially, and we try to filter the space with the exact senses. So basically, if we take a word like bank, it can be have noun and verbs. So based on the word usage, which is whether it is a noun or a verb, we try to filter out the sense from the sense space. Then we will be sending only the senses which is related to noun or which is related to verbs. Likewise, we are doing this sort of a sense reduction. Then we are passing some examples basically extracted from the knowledge base. So this is basically inspired from the RAG, where rather than using a retrieval, we are focusing on directly the word, and the word senses are passed as a few short cases to our model. Then we have the stepwise approach, but the model need to be followed in order to identify the our final sense ID. So we have asked to return multiple sense ID. If it says like there can be multiple sense IDs based on the confidence level. So the model or the setup, what we have followed here is we have evaluated open source LLMs as well as commercial LLMs. So for the open source LLMs, we have used Together AI API for the response generation part, and for the commercial LLMs, we have used Gemini API as well as the OpenAI API. So the temperature for these models is kept as 0, and the maximum token return is kept as 500. Then the evaluation data has been used as evaluation fuse dataset, where we have extracted 1050 random instances, which is like 40% nouns, which is 400 instances, 300 instances from verbs, 300 instances from adjective for the initial evaluation of this particular task. So the evaluation metrics we use here is the accuracy, which is the correct prediction divided by total predictions, which is similar to the F1 score also in this scenario, because all our sense IDs are unique in this approach. So when we go to the results and discussion, so this is from our previous study, which is under review process. Here we use different multiple and computational techniques in order to identify what is the optimal prompt. So we have evaluated the baseline LLM, which is in this study, which was GPT 3.5 turbo model. So we have evaluated different prompting techniques by incorporating different knowledge bases, so that we identify the prompt augmentation which we use for the incorrect prediction give us the best results. So this prompt has been used to our all other models. So this is the final results of this particular discussion. So all these models are chat models or the instructional models. So we have evaluated GPT-4 Turbo, 3.5 Turbo, Llama 370B, Llama 270B, Gemini, Y134B, Gamma 7B, and Mistral 7B. These models has been evaluated upon that evaluation dataset. So we have seen GPT-4 outperforming the prediction level, and the Llama 2 shows us promising results when it comes to the suggestion level. So this suggestion level is mainly aimed with 2 confident answers. But when it comes to the prediction level, which obviously Llama 3 70B model outperformed the Llama 2 70B model when it comes to the prediction level, which is the most confident answer is getting predicted as the first answer. So as and results and the discussion, we could see GPT-4 outperform the prediction level. And when it comes to the open source arena, Llama 3 model shows us a promising results, where it shows us a different domain that we could further fine tune and see how Llama 3 models can be further incorporated for WSD task. Then performance-wise, post-text nouns are shown promising results. Basically, nouns are easiest for all the models to identify compared to the adjective and words. Then for the future works, so there is a potential for the expansion. So fine-tuning open source model can be done in order to make it for the downstream tasks like WSD, so make it specific. And testing different techniques for edge cases. So there are quite a lot of edge cases what we need to handle. So currently we are in the process of testing on the edge cases. We have tested multiple approaches, and currently we are in the process of documenting and submitting into publications. So then scalability wise, we need to test with the Semco and Semsible. So for the initial study, we fit with the Fuse dataset, because Fuse dataset is a dataset which is mainly targeting on low frequency or frequency wise less frequency WSD words. But when it comes to Semco, it's sort of like a general WSD framework for the evaluation. So we are in the plan of evaluating it for our approach for the SEMCO and SEMCEVAL, which is MEVAL approach. Then the parameter tuning techniques can be further incorporated by introducing synonyms and space-based filtering methodologies. So the total contribution of the study is performing a quantitative evaluation on LLMs on mainly WSD tasks. Then we have proposed an effective hybrid model, which we use knowledge base and an LLM to identify the sense of a particular ambiguous word. And we have shown that LLMs are much capable on handling the lexical ambiguity across the post tags. So this is the acknowledgement. So we would like to express our gratitude to OpenAI Research Access Program. They are giving us and providing us credits, supporting the development of this project. So that's pretty much it related to this topic. Thank you so much. So if you are having any sort of question, I'm happy to answer.
Yeah. Thank you, Deshan. Let's see very quickly whether we can take one or two questions and then we'll call it off. Okay. Any questions?
Sure.
You want to ask any questions? Audience? Any questions?
Thank you very much for the talk, Deshan. Really, really interesting. I want to jump in on one of the observations you had there about different part of speech tagging words and the different word sense disambiguation going on there. You noted that nouns seem to be relatively handled well by the LLMs, whereas other part of speech struggled a little bit. I wonder if that has to do with perhaps the number of differences, the number of different meanings something like a verb can have as compared to something like a noun. Do you have any thoughts on that?
I'm not clear about the question. Can you please repeat it?
So you noticed in your results that LLMs tend to handle nouns better than verbs, for example. And I wonder if it's because the nouns generally have a short list of different meanings, whereas something like a verb can have many, many different meanings. For example, run could mean a variety of things. I wonder if you've got any thoughts about that, or if there's anything you could do, anything you might be planning for that in future.
Yeah, so basically in this study, we were mainly trying to identify how these LLMs can do the WSD. So in as a future aspects, currently we are working with in integrating synonyms, and we have reframed this WSD approach in an approach like iterative binary classification, and we have proposed a new approach called predict and verify approach. So currently we are in the process of publishing the work. That's why I'm not giving the numbers here. So basically I could say we are having the best results in the literature so far in WSD related to the few short WSD data. So currently we are in the process of publication, so you will be able to see the results soon.
Understood. Thank you very much, and good luck with publication.
Thank you so much.
Thank you very much, Deshan. We'll call it because we have had yours is the 6th presentation, and then we break for lunch now. Thank you very much for coming from
Thank you so much. Thank you so much for inviting.
Thank you. Okay, I think that ends the morning session. Then we'll break for lunch. Can we come back at 2:15? Lunch is served upstairs. 2:15 here. We have 3 more presentations.
Record.